Imagine this. You're scrolling through the news, and you see a headline that it sounds like it's straight out of a sci-fi movie.
Right.
A single chip made by Google solves a problem in 5 minutes.
Okay, 5 minutes. Fast.
But get this. The same problem, if you gave it to the world's fastest supercomputers. Their math says it would take longer than the age of the universe to finish.
And not just a little longer. We're talking 10 septillion years. That's a 10 with, what, 25 zeros after it?
It's a number that's basically designed to break your brain.
It is. It's astronomical. And the implication there is, well, it's profound. It suggests we're right on the edge of a new kind of computing power that just completely redefines what's even possible.
Exactly. It's not just about doing things faster.
No, it's about solving problems that we thought were fundamentally unsolvable by, normal computers.
So that's the big question. Is this dramatic claim real science? Or is it just science fiction? Is this a genuine breakthrough that actually changes the timeline for practical, scalable quantum AI computing?
And that's what we're here to figure out.
Right. That is the mission of this deep dive. We are going to look right past those crazy headlines and dig into the detailed research around Google's Willow chip.
We're talking the cold, hard, technical specs, what the rest of the community, the skeptics and the fans are saying.
We're here to help you separate that dizzying hype, the 10 septillion year claim, from the actual verifiable engineering progress. What did Willow really do? And what does it actually mean for the future of our security? For AI, for everything.
It's a huge topic.
It is. And on that note, get ready to absorb some serious knowledge. Welcome to InfoSec Bytes, your go-to source for bite-sized insights on information security, AI, cloud, quantum, and cybersecurity, incident root cause analysis. With over 100 episodes, we've got you covered on the latest trends and tips. Please like, subscribe, and share to join the conversation on various platforms: Spotify, Apple Podcasts, YouTube, Amazon Music, and stay secure. Okay, so let's start with the timeline of these claims, because the way Google rolled this out, it almost feels like a two-act play.
It really does. Act 1 was the big, flashy debut.
That was back in December 2024. It all started with a detailed blog post from Google.
And that initial announcement was all about setting this unbelievably high bar for speed, right? Hartmut Nevin, he's a VP of engineering there, he called the Willow chip an inflection point for quantum AI computing.
That's a bold statement. An inflection point.
It's a declaration. It's designed to make everyone, from investors to their rivals, stop and pay attention.
And the specific benchmark they used to back that up was something called random circuit sampling, RCS.
Right, and they claimed their chip did it in 5 minutes.
Which is where that insane classical estimate came from, that 10 septillion year calculation.
Yeah, and that single massive number, it did its job. It was in headlines everywhere, immediately. But it also, it sparked a lot of cautious plotting from their rivals.
So why lead with that number? I mean, the research we looked at suggests it was kind of a necessary marketing stunt, even if it brought a lot of criticism with it.
You hit the nail on the head. Why lead with this theoretical, almost abstract idea of speed? RCS is basically the quantum equivalent of showing off the raw horsepower of a concept car.
One that can't actually drive on real roads.
Exactly. It proves quantum supremacy, that you can do a task a classical computer physically cannot. But the critics jumped on it immediately. They said, okay, great, but it's a useless task. You solved a problem that nobody but a quantum physicist cares about.
So they needed that giant number to shock the market, but it left them open to the big question. Okay, but can you do something useful?
And that brings us to Act 2, 10 months later, October 2025.
Right. They come back with a paper in the journal Nature, and this time, they've completely moved away from that abstract RCS benchmark.
They pivoted hard to what they started calling verifiable quantum advantage.
And this experiment was totally different. They used a new algorithm called quantum echoes, and they ran it on 65-qubit circuits.
It was a very strategic move. They chose a task that's actually relevant to a specific area of scientific research, not just, raw number crunching for the sake of it.
And this is where the speed advantage got real. It became something concrete, something you could actually defend against a real-world machine. So tell us about that comparison.
Okay, so the quantum system, Willow, it collected all the data it needed in just 2.1 hours.
2.1 hours.
A key part, the verifiable part, was comparing that to how long it would take the Frontier supercomputer to simulate the exact same task.
And Frontier is, what, one of the most powerful classical computers on the planet.
It is, state of the art. And the estimate for Frontier to do the same job was about 3.2 years.
Wow. Okay, so from 2.1 hours to 3.2 years, that's a staggering difference.
And it's quantifiable. You can check the math. It works out to a 13,000 times speed
A
edge.
13,000x advantage.
Exactly. And that very specific, very real number is what allowed Sundar Pichai to call it the first verifiable quantum advantage. They shifted from a theoretical gap of septillion years to a practical, measured time-saving tool.
It's no longer just a party trick.
It's an operational tool with actual utility. And the media coverage reflected that. The initial skepticism kind of melted away after the Nature paper. Even the cautious researchers had to admit that Willow had, and I'm quoting here, reset expectations for quantum timelines.
But the skepticism isn't totally gone, right? I mean, this brings up the whole challenge of benchmarking in the first place.
Absolutely, and it's healthy skepticism. A 13,000x advantage sounds amazing, but you have to remember that classical computing isn't just sitting still.
That point.
Researchers are constantly developing smarter classical algorithms. Someone could, in theory, find a clever shortcut tomorrow that shrinks that 3.2-year simulation time down significantly.
So that 13,000x margin could get smaller.
It could. The real test for quantum systems isn't just an initial speedup. It's proving a fundamental scaling advantage that holds up over time. Otherwise, they're just in a constant race with Moore's law and human cleverness.
Which is why the stuff we're about to get into, especially the error correction, that's actually way more important than the 13,000x number itself.
That's the real breakthrough.
Okay, let's really unpack this idea of verifiable advantage, because this gets to the absolute heart of what scientists care about and why it's a much bigger deal in the long run than that first RCS claim.
Yeah, we have to start by acknowledging just how much criticism that first benchmark, random circuit sampling, really got.
As we said, it was basically a math problem designed to be impossible for regular computers.
Right, because the complexity just explodes exponentially. But critics rightly called it academically isolated. It solved a problem that had no practical application.
The research had a great analogy for it. It's like calculating pi to 5 million digits on one of the first mechanical computers.
I love that.
Yeah, it's super impressive to the engineers who built the machine, and it proves the machine works, but it's totally meaningless for ordinary people trying to solve real-world problems.
Verifiable advantage is the answer to that. It closes that utility gap. And that's why the pivot to the quantum echoes protocol was so important. It gives you a result that actually means something to physicists.
Okay, so to get a little technical then, what is this quantum echoes protocol actually solving? Why this specific algorithm?
So at its core, quantum echoes is a physics experiment. It's designed to measure something called out-of-time order correlators, or OTOCs.
OTOCs, that sounds complicated.
The name is a mouthful, but the concept behind it is actually pretty cool and really important.
Okay, break it down for us. What do OTOCs measure?
They describe a process called information scrambling.
Information scrambling.
Yeah, think of it like this. Imagine you have a perfectly clear swimming pool, and you drop a single drop of blue dye into it. At first, that dye, that's localized information.
Right, it's all in one spot.
Scrambling is the process of that blue dye spreading out through the entire pool until you can't tell where it started. It's become indistinguishable from the rest of the water. OTOCs measure how quickly and how thoroughly that original information gets dispersed across all the interconnected qubits in the system.
So you're basically tracking how information spreads out and gets randomized inside the quantum computer over time. Why is that important for scientists to measure?
Because information scrambling is tied to some of the deepest questions in physics, especially in an area called condensed matter physics. Scientists use these measurements to study how really complex quantum systems evolve, things like high-temperature superconductors or other exotic materials.
Can you give us a concrete example of why that matters?
Sure. One of the most famous applications is studying what's known as quantum chaos. And this is going to sound wild, but it even connects to the physics of black holes.
Black holes.
Yeah. Black holes are considered the universe's ultimate information scramblers. Now, Google isn't simulating a black hole with their chip, but the underlying math that governs how information scrambles in a complex system of qubits, it's the same kind of math physicists use to understand how information might escape or not escape a black hole.
So it's a tool for fundamental physics research.
Exactly. And more practically, in materials science, understanding scrambling helps you design materials with specific properties, like how they conduct heat or electricity. It makes the result of the experiment a measurable, repeatable, observable. not just some black box answer from a computer.
That makes it scientifically sound. It's a real physical thing being measured, not just a calculation. You could try to see the same effect in a university lab, even if you couldn't simulate it at the scale Google did.
That's the foundation of scientific credibility, and Google really leaned into that by committing to open science.
Right. The research pointed out they did more than just publish the paper. Tell us about that.
This was huge, and a major difference from the first claim in 2024. When the Nature paper came out, Google also published the raw circuit data from their experiment and the classical simulation scripts they used to get that 3.2-year estimate.
So they basically put all their cards on the table.
They did, and it's crucial for two reasons. First, it invites everyone, academics, their rivals, any skeptic out there, to check their work. And second, it solidifies the benchmark itself.
They're essentially saying, here's our work, here's our data, here's the classical calculation that says this is hard, now you go try to beat it.
Precisely. This kind of verifiability builds confidence in the results. It allows other researchers to run cross-checks on their own quantum devices, whether it's from IBM or Quantinuum, or it lets classical computing experts try to find better algorithms to shrink that 3.2-year number.
So it moves the whole debate forward.
It does. It moves the conversation from, can you even do this, to, okay, how reliably and how efficiently can we all do this? It turns the Willow chip into a trustworthy tool for the whole quantum ecosystem.
All right, let's get into the actual engineering, the nuts and bolts, because this is where you start to understand just how incredibly difficult it is to build one of these things. Let's start with the core architecture, these things called transmon elements.
Yeah, transmons are kind of the workhorse for most of the leading superconducting quantum computers right now. The Willow processor has 105 of them.
And what is a transmon, basically?
You can think of it as a tiny superconducting circuit that's engineered to behave like an artificial atom. It has energy levels, just like a real atom, which is what you use to create the qubit. They're designed specifically to be less sensitive to certain kinds of background noise.
And the big trade-off with using them is
The cold. The immense, insane level of cold you need. Superconductivity only works at temperatures just fractions of a degree above absolute zero.
So that's why you always see those pictures of quantum computers that look like giant golden chandeliers.
Exactly. That's the cryostat. It's a massive, multi-stage refrigerator, and the research notes are really telling detail. Of the 105 transmons on the chip, only 103 were actually operational once it was cooled down.
2 of them just didn't work.
Right. Which sounds small, but it shows that even at this scale, getting a perfect yield is basically impossible. It just underscores that this is still highly laboratory and very expensive technology. It's nowhere near being in a normal data center, let alone on your desktop.
Okay, so the next critical spec, and maybe the most important measure of progress, is stability. Qubit coherence.
Right. This is all about how long a qubit can hold on to its fragile quantum state, the superposition, the entanglement before the outside world messes it up and destroys the calculation.
I like to think of it as the quantum computer's attention span.
That's a perfect analogy because that attention span directly determines how deep of a calculation you can run. The main measurement for this is called the T1 relaxation time.
Longer is better.
Much better. The research says the median T1 time for Willow is about 106 microseconds.
106 microseconds. I mean, a microsecond is a millionth of a second. That sounds unbelievably short. Why should we get excited about that?
It is incredibly short in human terms, but in the quantum world, it's a huge achievement. Early systems were struggling to even get to 10 microseconds. And the real engineering feat here is that Google scaled up from their 53-qubit Sycamore chip to this 105-qubit chip while maintaining that level of coherence.
So keeping the quality high while increasing the quantity.
Exactly. That 106 microseconds is just long enough to run what they call mid-depth quantum circuits. And crucially, without that level of stability, the error correction we're about to talk about would be physically impossible.
So we're managing quantum's bad case of ADHD just long enough to get some useful work done.
That's a great way to put it. And the research actually gives specs for 2 different Willow chips, which shows a really interesting engineering trade-off.
Oh, what was that?
So one chip, which was optimized for the error correction experiment, had a T1 mean of 68 microseconds. The other chip, optimized for raw speed on that RCS benchmark, had a T1 mean of 98 microseconds.
So they're slightly different. What did that tell us?
It tells us they're making very specific choices about the physical geometry of the chip. You have to wire these qubits together so they can talk to each other, but you also have to shield them from noise. If you optimize the layout for perfect shielding to get super high coherence, you might make it harder to link them up for complex operations.
And if you optimize for the best connections, you might introduce a little more noise and lower the raw coherence time.
Precisely. The fact that they're navigating these tiny, nuanced hardware trade-offs with such precision shows this is moving beyond pure science and into real industrialized quantum engineering.
Okay, so beyond coherence, we have to look at gate fidelity and error rates. This is about the accuracy of the basic operations. This is where you measure reliability.
And this is arguably the most critical number for actual computation. If your basic operations are sloppy, the errors just pile up and your final answer is garbage.
So what are the numbers for Willow?
The really tough ones, the entangling gates that link two qubits together, have an average error rate of about 0.15%.
0.15%.
Yeah, and the single qubit gates are even better, around 0.036%.
So what does a 0.15% error rate mean in the grand scheme of things? Is that good enough?
It's extremely good. The general consensus in the field is that for the type of error correction Google is using, the surface code, you need to get your two qubit gate errors under 1% and ideally well below 0.5%.
So they're clearing that bar pretty comfortably.
They are. Hitting a median of 0.15% shows their hardware is meeting and in some ways exceeding the prerequisites you need for robust fault tolerance. These numbers are what make the next part, the main scientific breakthrough, even possible.
And this is it. This is the moment we've been building up to. The real scientific accomplishment, the one that has researchers genuinely excited, is this idea of tackling the fundamental problem of the qubit. Its fragility. It's the successful demonstration of scaling error correction.
Yeah, to get this, you have to first appreciate how big the problem is. Qubits are just. They're incredibly noisy. They're sensitive to everything. Stray radiation, tiny changes in temperature, even physical vibrations. They lose their quantum state or decohere extremely fast.
And the research pointed out something counterintuitive. If you just use raw, unprotected qubits, making your computer bigger with more qubits actually makes it less reliable.
Right, because you're just adding more points of failure. The result can be fundamentally wrong. So the goal isn't just about speed, it's about being right. A useful quantum computer has to be right enough of the time.
And that requires error correction.
Exactly, and this is where Google's experiment is such a monumental step. They successfully demonstrated the scaling behavior you need for error correction to work. In the field, they call this achieving a state below threshold.
Okay, below threshold. Can you give us an analogy for that? What does that really mean?
I think the best way to think about it is like the early days of aviation. For years, people were building these flimsy gliders or machines that tried to get off the ground. And the problem wasn't just lift, it was control.
Okay.
Every time they added more parts, a heavier engine, more complicated controls, they were just introducing more things that could break. If your system is above the error threshold, adding more qubits to try and protect your data is like strapping a bigger, heavier engine onto a rickety wooden plane.
It just guarantees a faster, more spectacular crash.
Exactly. So being below threshold means you finally built a system where adding more complexity actually makes the whole thing more stable, not less. It's the difference between that glider that crashes and a modern jet engine that actually becomes more efficient and stable as you scale it up.
That's a fantastic analogy. So Google proved their system is like the jet engine, not the glider.
That's what they proved. They showed that the background noise in their hardware is low enough that when they use more physical qubits to encode one stable, protected logical qubit, adding more of those physical qubits actually reduces the error rate of that logical qubit. This validates the entire theoretical roadmap for building a reliable quantum computer with this method.
So tell us about the actual experiment. How do they show the scaling?
They built and tested progressively larger arrays of physical qubits using something called the surface code layout.
The surface code.
It's this intricate 2D grid of qubits. Think of it like a checkerboard. They scaled this grid up from a 3x3 array to a 5x5 array, and finally up to a 7x7 array of these encoded qubits.
So as the grid got bigger, a single logical qubit was being protected by more and more physical qubits. What happened to the error rate?
This is the golden result. With each expansion of that grid from 3x3 up to 7x7, they cut the overall error rate in half.
In half every time.
Every time. That's an exponential reduction in the error rate. This isn't just a small linear improvement, it's an exponential one. It means as they keep scaling, the error rate should drop rapidly towards zero. As Hartmut-Neven said, it's a historic accomplishment because it proves the physics of fault tolerance can work in the real world.
That's huge.
Yeah.
This wasn't just a simulation on a supercomputer. This was a physical experiment confirming that their hardware is clean enough to support the surface code and that the theory actually works.
It does, which brings us to the really important discussion about physical versus logical qubits and, the real cost of getting this kind of correction.
Right, because if you need a 7x7 grid, that's 49 physical qubits, just to create one single reliable logical qubit, that's a very high overhead.
It is, and that's the central challenge. The research notes that in the past the numbers were even worse. But Willow's success shows they're on the right path to making that cost manageable. They actually have a metric for this. They call it lambda $3 and so lotters, and the value they got was 2.14.
So what does that number, that lambda, tell us?
For the listener, you can just think of it as a measure of how efficient the error correction is as you scale up the grid size. The crucial thing is that the number is greater than 1.
If it was less than 1, that would mean adding more qubits was actually making things worse.
Exactly. A number bigger than 1 proves that scaling up is providing a real benefit, that you're suppressing errors much faster than you're introducing them. Willow's high value here proves they are efficiently turning noisy physical qubits into a reliable logical one. They're showing a path where the power of your logical qubit starts to grow much faster than the number of physical ones you need to protect it.
And that's the real difference between a lab milestone and a practical blueprint for the future.
That's the ballgame.
So a breakthrough like this, one that basically validates a core scientific roadmap, it's going to send massive shockwaves through the tech world, the investment world. Let's talk about those reactions.
Well, the reaction was, as you'd expect, pretty polarized. On one hand, you have the Google team and their supporters celebrating. On the other, you have a lot of cautious scrutiny from the rest of the scientific community.
Right.
We saw commentary in Nature praising the experimental rigor of what they did, saying the transparency was a huge step forward. But at the same time, you had analysts reminding everyone, hey, this is still a fragile, super expensive piece of lab equipment sitting in a giant freezer.
But their competitors, they weren't just dismissing it as hype, were they?
Not at all, and this is really telling. The research explicitly says that rival teams at IBM and Quantinuum announced plans to try and replicate the Quantum Echoes protocol on their own machines.
So they're taking the benchmark seriously.
Very seriously. When your biggest competitors dedicate their own hardware and resources to copy your homework, you know you've set a new industry standard. The age of RCS as the key benchmark is over. Now it's all about quantum echoes.
And I'm guessing the investment money started flowing.
Oh, yeah. The hype cycle kicked back into high gear. Social media was buzzing, with both excitement and doubt. And that led to a whole new round of discussions in the venture capital world about, okay, what are the real timelines now for monetizable quantum services?
And this is happening even as people are warning about a potential bubble in the classical AI world.
Exactly. But the consensus seems to be that Google has just raised the bar for performance across the entire quantum industry. It's intensifying the arms race.
Okay, we have to talk about the elephant in the room, the big public concern, quantum and cryptography. Is the Willow chip or the one that comes after it going to break the internet?
It's a valid fear. It's totally rational. It all comes from our knowledge of Shor's algorithm.
Right.
Shor's algorithm, once you can run it on a big enough quantum computer, will be able to efficiently factor the large prime numbers that all of our modern public key cryptography relies on. We're talking about RSA, the thing that secures almost all secure web traffic.
And the idea of that being broken is, well, terrifying. It's the source of this long-term quantum dread.
It is. But we have to keep the threat in perspective, especially when you look at Willow's 105 operational qubits.
So what's the scale we would actually need?
Well, the research cites a popular number for a really destructive capability, like being able to hack the cryptography that secures Bitcoin wallets. The estimate for that is that you'd need more than 13 million stable, error-corrected qubits.
Okay, let's just pause on that. Willow has 105 physical qubits, some of which are needed to make one logical one, and we need 13 million error-corrected logical qubits.
The gap it's staggering. It's 5 or 6 orders of magnitude. Just try to imagine the size of the cryostat, the cooling power, the wiring you'd need for 13 million qubits, all working together perfectly.
So the reality check is?
The reality check is absolute. Willow cannot factor RSA today. It's not a cryptographic weapon. It's a scientific instrument for discovery. The security risk is real, but it's a long-term one. And that's why the work on post-quantum cryptography is so vital right now.
So the threat isn't for tomorrow? but the preparation has to start today.
Absolutely. We have to be migrating to new algorithms that are resistant to these future quantum computers. And it's also worth noting, the threat is mostly to that asymmetric encryption, like RSA. Symmetrical encryption, like AES, is generally considered a lot safer. You might just need to use a bigger key size.
The research also got into this sort of philosophical debate about what a quantum computer even is. And understanding that is so key. It's not just a faster version of the laptop you're using.
This is so crucial. A classical computer uses bits, right? Zeros and ones. It works through problems step by step. A quantum computer uses superposition, where a qubit can be a 0, a 1, and everything in between all at the same time. And it uses entanglement to link them.
So it explores this huge space of possibilities all at once.
That's the famous cheating analogy, that it just sort of magically finds the right answer. But the magic is just physics. It doesn't do billions of extra calculations in the way we think about it. It encodes the problem into a quantum state and then lets quantum mechanics evolve that state so that when you finally measure it, it collapses to the right answer.
It's a fundamentally different way of computing.
It is. It's an optimization engine at its core. And that's why it's only useful for very specific, very complex problems and not for, checking your email or running a database. It's a totally different philosophy of computation.
So let's assume this exponential error correction scaling continues, and that's the big billion-dollar assumption. What are Google's projections? When do we get those all-important logical qubits, and what are the first real-world problems they'll be able to solve?
Well, the projection from Google is that if they can keep up this rate of improvement, then truly stable, usable logical qubits could arrive within several years.
Several years. It's aggressive.
It is. It's not a guarantee, obviously, but it makes that general decade-long timeline for truly fault-tolerant quantum computing feel a lot more certain, less like science fiction.
And their first target applications? They're not going after small problems.
No, they're aiming for the huge, computationally dense areas where classical computers have already hit a wall. First on the list is molecular simulation and materials design.
So designing new chemicals or materials from the ground up.
Exactly. Modeling complex chemical reactions is just impossible for classical computers beyond a certain very small scale. But a quantum computer could, for example, help design new catalysts, or maybe new materials for solar panels that could dramatically increase their efficiency.
Can you give us a really concrete example of that?
The classic one is the Haber-Bosch process. It's the industrial process we use to make ammonia for fertilizer. It's incredibly important for feeding the world, but it also consumes something like 1 to 2% of the entire world's energy supply.
Wow.
If a quantum computer could accurately simulate the molecular dynamics, we might be able to design a catalyst that could do the same reaction at room temperature, without all that heat and pressure. The energy savings would be phenomenal globally.
Okay, so materials design, what else?
The other big one is energy optimization.
Like managing the power grid.
Exactly. Or optimizing massive global supply chains. These are problems with a near infinite number of possible solutions, and you're trying to find the single best one. Quantum computers are just inherently designed for that kind of optimization problem.
But the path to get there is still full of massive hurdles. We've conquered a huge scientific one, but now the engineering challenge looks just as big, if not bigger.
The hardware hurdles are definitely daunting. The first is just scale and uniformity. You need to go from 100 qubits to thousands, and eventually millions, and they all have to be nearly identical and perfectly reliable.
Remember, even on this chip, 2 out of 105 didn't work.
Right. Now imagine that problem scaled up by a factor of 10,000, and then you have to wire them all and control them, all while keeping them at a temperature colder than deep space. It's a daunting hardware engineering task.
And the cryostat itself, the refrigerator, becomes a huge problem.
A colossal one. Scaling up the cooling systems needed for thousands or millions of qubits is a massive mechanical engineering challenge in its own right. So while we're optimistic, the research is clear. It's estimated to take at least another decade to be truly practical. And that's, assuming things go well.
And all this just highlights how important it is for other people to validate these results. Which brings us back to our listener. What does this mean for the professional who needs to understand this today?
Well, the credibility of this whole field really depends on that replication need. Independent labs have to be able to reproduce these quantum echoes results on different types of hardware. That's what turns a Google breakthrough into a scientific fact.
And having those open benchmark scripts is key to that.
It's essential. It ensures a fair comparison, so we know we're not just seeing classical algorithms get better and quietly catch up.
So for the professionals listening in, logistics, finance, healthcare, how do they get ready for this quantum-driven future?
I think they need to start understanding the architectures that are being proven out right now. The people who are following the standards, the algorithms, the different types of qubits today, they're the ones who are going to be shaping tomorrow's solutions.
It's about building foundational knowledge.
It is. The research mentions how important it is to enhance your expertise, to be able to evaluate these new kinds of workloads and how they'll integrate with the cloud. Things like the AI plus healthcare specialist certification that was mentioned. That kind of upskilling is how you prepare to design systems that are quantum ready, not quantum vulnerable.
Okay, let's wrap this all up. Let's boil this deep dive down to the two most important foundational takeaways about Google's Willow chip.
Okay, first, and this is the big one for the scientists. Willow is not useful for you and me today, but it achieved a monumental scientific breakthrough in exponential error suppression.
That's scaling proof. Cutting the error rate in half every time they made the grid bigger.
Exactly. It experimentally proves that the theoretical roadmap for building a reliable, fault-tolerant quantum computer actually works. It makes the future engineering challenge look incredibly hard, but fundamentally, it looks achievable.
And the second big takeaway.
Second, Google successfully changed the conversation. They moved us away from abstract, sensational benchmarks, that 10 septillion year claim, to a verifiable quantum advantage with the quantum echoes protocol.
They gave us a real, measurable scientific result, a 13,000 times speed up over a supercomputer that other people can now go and test.
Right. It shifted the field from hype to rigorous lab-validated science. It set a new bar that everyone else now has to clear.
And to leave you with one final provocative thought to chew on.
The research suggests that while Willow itself can't break our current encryption, the pursuit of quantum computing is forcing the entire world to make a choice about our cryptographic future, and we have to make it now.
That's the choice.
We're basically being pushed into one of two futures. Either we adopt cryptographic keys that are so incredibly large they become impractical for our current systems to handle, or we have to invent and deploy entirely new quantum-resistant security systems from scratch.
So we're watching the blueprint for the future of global security being designed right now.
We are. And whether it succeeds or fails depends on the progress of chips just like Willow.
That is the ultimate high-stakes deep dive into the future. Thanks for tuning in to InfoSec Bytes. Keep exploring our 100-plus episodes on information security, AI, cloud, quantum, and cybersecurity incident root cause analysis. Please like, subscribe. We are on various platforms, Spotify, Apple Podcasts, YouTube, Amazon Music, and share to stay connected and keep your cyber defenses strong.